quantum field theory and statistical physics in the 50s were rapidly developed and converging to each other. First step, I would say, was a remarkable analogy between quantum field theory and statistical physics. Dirac and Feynman established some of our histories in quantum mechanics analogous to statistical sum. And it was Julian Schwinger who noted that inverse temperature in statistical physics is equivalent to imaginary Minkowski time in quantum field theory. So this is these are my heroes: Paul Dirac, Richard Feynman, and Julian Schwinger, who in different ways contributed to this remarkable analogy and this heroic development of quantum field theory. Now, then, in the 50s, it was pronounced dead by Heisenberg and Landau. And Landau basically declared the epitaph. He said, the Lagrangian field theory is dead and should be buried with all the proper honors. The cause of death, Moscow zero. Virtual pairs completely screen the physical charge in quantum electrodynamics so that this charge vanishes in the local limit. So this is Heisenberg in late years of his life and Landau in some middle years before the catastrophe. And I would say that with all my admiration to both of these people, they, at some point in their life, served as the block to the new physics development. It's like, you know, the heroic figure, the great warrior falling on the narrow path and blocking the way to the whole army. That happened to Heisenberg and to some extent to Landau because of this, you know, I would say arrogant declaration that quantum field theory is dead. And by the way, as my good friend and former student Sasha Polyakov said, they buried Lagrangian field theory, but they forgot to drive the stake through the heart. So it revived. Anyway, in the 60s, in spite of quantum field theory pronounced dead, some researchers couldn't stop thinking about this analogy because it was correct. One of them existed, another didn't, and they didn't know what to do, but they kept thinking. And the thought cannot be stopped. So statistics continued to imaginary time is the same as relativity theory with this Minkowski imaginary time. That's true. And then let's just hope that Moscow zero can somehow be avoided in elementary particle theory. And these brave researchers, Larkin and Vax, I couldn't find the photo of Vax, Nambo and Leon Lassina is present here, developed an analogy between elementary particles and statistical physics. They understood that that goes much further than just this observation of Schwinger about imaginary time. It is a lot of phenomena like vacuum structure, spontaneous symmetry breaking specifically, the most interesting phenomena in statistical physics, also should apply to elementary particles. And Tola Larkin, who was, by the way, a student of my father, and at some point my friend Sasha Polyakov and myself were also students of my father in some spiritual way, because he didn't teach us anything, he just inspired us. And so did Tola Larkin. Tola Larkin inspired us to study spontaneous symmetry breaking in the Young-Mills theory. Tola Larkin was a remarkable man. He was very talented, very sharp, but infinitely selfless, and I would say even lazy, because he was not lazy to think things through, but he was lazy to present them and get credits. He was just interested in truth. Remarkable person. Anyway, he inspired us to study it, and we jumped into with young vigor. We were 17 years old. And of course, all of us impliedly implied hope that the Moscow zero can somehow be avoided in this theory. We didn't know how. We just were ignorant and brave because of our ignorance, and we just jumped into that and said, what if, and started making hypotheses, crazy ideas, and then we kept going and going and arrived at something. So in 64 to 66, we tried to publish our findings, and Journal of Experimental Theoretical Physics refused to publish our work. So here is the photo of Sasha Polyakov on the left in red circle, and me on the lower right in blue circle. That's us in the obligatory military training after, I believe, third year in Moscow Physical Technical Institute. That's about the time, maybe that was next year after we developed the theory. Anyway, that's us, and these are to our friends. And our work paper was called Spontaneous Symmetry Breaking of Strong Interaction and Absence of Massless Particles. It's right to the point. That's the essence of this Higgs mechanism. And we dreamed it up in 63, tried to publish in 64, and then eventually published in 66 because of refusal of JATP and because of efforts of this guy, Vladimir Mikhailovich Schechter, who was a Gribov's student, and he was at that time associate professor or something in the lab headed by Gribov. So basically, Gribov was behind these objections to this theory, and his objections were not personal, it was ideological. He was a follower of Landau, who was a follower of Heisenberg, and they thought that local field theory is killed, doesn't exist. You should not even think about some spontaneous symmetry breaking. These are forbidden thoughts, forbidden notions. That's how it was. So the story of spontaneous symmetry breaking, and it is interlaced with my Siberian rafting, that story is quite dramatic and instruction. Two boys went against their teachers and suffered for the truth. They could have broken us, but we survived, although the scars remained. By the way, these teachers never showed remorse, gratitude, or apology, though they have spent the rest of their careers with spontaneous symmetry breaking and gauge theories. We haven't heard thank you, we haven't heard we're sorry, we haven't heard, oh, you guys must be getting some prize or some praise or something. No, nobody mentioned that after the fact. I vividly remember Sasha seeing me off at the train station for the hiking trip in Siberia in the summer of 63, around June. I remember that because on this hike, on my 18th birthday, I nearly drowned in the river called Mana near Krasnoyarsk in Siberia. My girlfriend and I were sleeping inside a folded tent on a raft, which was in the middle of the night, foolishly, rafting along the river, and then our raft hit a huge pile of logs and immediately went under, leaving us split seconds to wake up, disentangle, and get to the surface. So my guardian angel tried his best and saved us. So we climbed out, and then we spent the night and the middle of the next day until one day later, geologists rescued us from this pile of logs. So that day, at the train station, Sasha and I argued about spontaneous symmetry breaking until the train departure. So I vividly remember that because he presented argument why spontaneous symmetry cannot happen, and I couldn't object, and I was thinking about that whole time. Maybe that helped me survive. Anyway, after my survival in Siberia and return to Moscow, we jumped back into work and proved that massless particles are unobservable in gauge theories. So there is an exception from the Goldstone theorem, which would say that there must exist such massless particles. Turns out that these massless particles become the unobservable longitudinal components of vector mesons. So that was the essence of Higgs mechanism, as it is now called. We title our paper Spontaneous Symmetry Breaking of Strong Interaction and the Absence of Massless Particles. Essentially, it pertains to then unknown QCD, the theory of strong interaction, where massless gluons are unobservable as we claim. So there were 3 submissions. We sent the article to JTP in the fall of 63 or winter of 64, a year earlier than anyone else. Then a reviewer started to torment us. I now know who it was, Vladimir Schechter, an associate of Gribov. How he mocked us. Essentially, he was simply wrong and didn't understand basic quantum field theory, but from the height of his anonymity, he wrote, "The authors will have to revise the article again, perhaps lamenting the reviewer's ignorance," which we did and still do. Judging by this phrase, and I remember it for a lifetime because it was so insulting and I felt so helpless. It was already in the second negative review because it says again, revise again. So in JTP publication, it says submitted to JTP editor November 30, 65, resubmitted February 6, February 16, 66. That means that there were 3 submissions because this phrase was in the second submission, which was rejected, and then there was the third one. So second one was November 30, 65, and third one was February 16, 66. But the first one was apparently somewhere in 64. And because that's when we finished the work, 63, 64. So that manuscript vanished. This means that the first manuscript was lost. It was submitted to the editorial office in 64, was rejected by Schechter, then resubmitted in 65. You see, each submission take almost a year because you have to spend a few months in Glavlit. You have to submit your paper first to the censorship. It's called Glavlit. After they clear it, of course, they understand nothing. They just sit on that. After they clear that, then you submit the journal. So it took a year, 64, 65, 66. That was reviewed by Schechter again, rejected second time, and finally was resubmitted and accepted in 66. The phrase is from the review of the second manuscript. Obviously, it was the first manuscript that he rejected before that. Where is this first manuscript? It was only possible to send it to JTP after getting permission from Glavlit, which took a couple of months or even half a year. So it was sent to Glavlit somewhere in the fall of 63 or winter of 64. Neither Glavlit nor JTP could find it. When I tried to find our lost manuscript in 2013, the JTP told me they burned all the old manuscripts a year before. Now, this is already a blank spot in the history of physics. You know, there is a famous phrase from the classical Russian book, Master and Margarita by Bulgakov, which was attributed to Volan, the Mephistopheles. The manuscripts don't burn. Unfortunately, this one burned. Or maybe it is hiding somewhere. Maybe the daughter of our referee Schechter, who is still alive, is, storing it somewhere. Maybe Glavlit has it somewhere. I just gave up. I have more interesting things to do than to help history of science, because it's much more fun to make new discoveries than fight for the old ones. Anyway, I hope you hear me, guys. Do you hear me? Please respond. Hello?
We hear you. We hear you.
Okay.
Yes, yeah, we hear you.
Because I expected questions and objections or laughter or something, but nothing, just silence. I took this silence as loss of hearing. But anyway, so blank spot. Now let me give you a little bit of background why quantum field theory, which is such a natural thing now, was so considered as heresy and kind of almost forbidden in that time, 50s and 60s. See, Heisenberg declared that physics must only study observable quantities, not just compute observable quantities, which of course is obligation of physics, but it cannot rely its computation on anything which is not observable. You have to only seek relations between observable things. So like if you're pulling the rabbit out of the hat, you're not allowed to ask questions, was it there in the hat? How many rabbits are there? You only can compute how far it will jump and in what direction. That's called S matrix or scattering amplitude. So this S matrix was perfected by Regge, Chu, and Frauche before being buried in the 70s after asymptotic freedom. That's great Tullio Regge, that's Chu and Frauche. They developed very powerful technique, which is quite useful because sometimes you really don't need to go into microscopic theory and understand what is inside. Sometimes you can just use general properties, and these are very important properties, analyticity, unitarity. I'm using it myself very often. And you could compute things like asymptotic behavior of scattering amplitudes. I remember when I was visiting CERN, that was last time before KGB closed all my travels after me being impolite to the KGB curator who tried to recruit me. So that was my last visit to CERN before ban my travel. I was invited by, who was that? Kubini, I guess. No, maybe one of the, who was head of the physics department in CERN at the time. Anyway, he invited me to lunch because they wanted to invite me to become staff member, which I didn't understand. I didn't even say yes or no, because for me that was impossible idea. But anyway, during that lunch, he asked me, what do you think we should build? We have two projects. One is to build the collider, which would collide electron-positron or proton-antiproton pad, so they will, produce a lot of energy and go inside of something, inside particles. Or we should build the machine to study the peripheral collisions, which would allow us to verify the Regge theory, which was a theory of interaction at high energies, which were mostly peripheral, not going inside. I said, there is no question. You don't know what is inside. So if you build a collider, then you will study something unknown. You would continue the quest for the, the structure of nature. And with the peripheral, collisions, you would only check something which is known already, unitarity analyticity. That's not a hypothesis, that's a fact. So the fact you can compute something doesn't mean you need to check it. You have to check something which is unknown. So thank you. And then he invited me, and then and of course I didn't reply. And also KGB never let me go abroad again until I defected and ran away. But that's another story. So here is this S matrix dogma, and here is what happened in the 60s. I would say even up to the 70s with the whole elementary particle theory until there was microscopic theory based on quarks and asymptotic freedom, etc., etc. And funny thing is that now similar things are happening with turbulence. Again, stagnation, conservative phenomenological approach, and failed attempts and just refusal to study the microscopic theory. We'll come to that later in the second half of my talk. Let's talk about Landau's ideas on critical phenomena, because critical phenomena is what was the beginning of conformal field theory, which is second topic of my talk. So it started with Landau ideas. Unfortunately, he couldn't continue this work. It was terminated when he got into this tragic automobile catastrophe, and basically no longer was himself. His brain was barely alive after that. So Landau studied 3D field theory of fluctuations in critical phenomena. That's him, I think, after the catastrophe. You would see that he still has some fire left in his eyes, but the expression is not as lively as before, and it's clear that the guy is suffering. Anyway, what he observed was the so-called K3 halves law. It was the first attempt to get anomalous dimensions in the field theory. You see, this K3 halves is not really an anomalous dimension. It was a balance of powers in some model equation. It's called Dyson equation. If you consider Dyson equation and just take the first diagram for the self-energy part in the lambda phi fourth theory, which was basically the theory of the Ising model at that time. And then you would see that you could balance the power of propagator with these powers of 3 propagators in denominator, and the resulting power would be K3 halves. It's not anomalous dimension in a sense. There is no self-consistency equation. It is just the balance of powers. And that was important for Sept, but that was clearly not the solution. And he knew that, but he couldn't finish his work. Anyway, Pokrovsky and Potashinsky, my good friends, Potashinsky is no longer with us, but Pokrovsky is still alive. He is professor emeritus in Texas A&M University, and he is still trying to work, and he is, very good researcher. They took over Landau's work in the mid-60s. So here is Valery Pokrovsky. They summarized K3 halves idea. They developed it further and considered other diagrams of the classical field theory. They basically took the Landau's view that the Festenrichter theory is a classical field theory. They called it classical. That's in modern language, it's statistical field theory. It's the same as quantum field theory, because quantum field theory is no longer considering imaginary time. It's considering the same statistical sum as Gibbs ensemble. Anyway, Pokrovsky and Potashinsky summarized K3 halves idea, and they noted their logarithmic divergence. There was a problem. They didn't know how to solve that problem, but finding the problem is sometimes as important as solving it. Anyway, they did it. And then I was inspired by that work, and I tried to apply it to the Gribov's region field theory. That was the field theory which was allowed by the Landau School at that time. And I have to confess that I switched to that, partly to learn something new, which I did, learn a lot from Gribov, and also because it was an interesting new theory anyway. So I tried to apply this idea of the self-balanced anomalous powers to the Gribov region field theory. So that's me at that time, and that's Gribov. I had much more hair on my head, but apparently much less brain than Gribov, who was almost bald, but he was very sharp. But the only thing good about me at that time, that was I was thirsty for knowledge. I was learning from Gribov day and night, and we worked together very happily. Though initially he fiercely criticized my approach. He declared to his disciples in his lab, when he heard about me, first about this crazy ideas of spontaneous symmetry breaking, and then about this scale invariant regional field theory. He said, there is a new pathologist, Sasha Junior Migdal. And then I came to Leningrad. Pathologist, that was the way to scorn people who were developing some pathological theory, something which doesn't comply with the modern views of the Landau School, was called pathological, so it was called pathologist. But anyway, I came to Gribov, we started arguing, and at the end, we started working together. So he was, in that sense, flexible. He was, at the same time, he didn't have much intuition, but he had such a great brain that he, when presented with something, he understood and immediately realized how to develop that. So it was very interesting symbiosis. And we worked very happily together. We produced several works, and one of them was this scale-invariant region field theory. So here was the breakthrough, which I am quite proud of. It happened in winter of 66, I believe, 66, 67. I dreamed up the idea of adjusting the scaling index mu to get non-zero solution of homogeneous bootstrap equation. You see, at that time, we already knew in region field theory that the scale-invariant amplitudes are supposed to satisfy homogeneous equation because because these amplitudes by scaling power counting were larger than the Bayer term in the Schwinger-Dyson equation. There is the Bayer term plus what's called skeleton diagrams. Skeleton diagrams were all scaling the same as the left side, but and both of them were larger than the Bayer term. So there was homogeneous equation. Equation could be nonlinear, but homogeneous. Homogeneous means that you could, multiply it by some factor, and it will still be the solution. And that means also that there is always a zero solution. How come you don't have zero solution? Well, usually when you have homogeneous equation, you have to tune some eigenvalue. Like if you have like eigenvalue equation for the matrix or to operator in more general case, you have to tune some eigenvalue or some unknown dimensionless parameter to get non-zero solution. And I dreamed up idea that in our case of these bootstrap equations, which we don't know how to solve, and we had a solution with arbitrary indexes, you have to adjust the scaling index to get non-zero solution. So the index is to be determined from the solvability of the bootstrap equation. And that was a very fruitful idea. I immediately called Gribov, and he thought about that, and after a long pause, he agreed, Sasha, it might work. And the rest was just tedious computation. We jumped into that work, and then he was shining when, intuition was no longer needed, but just the analytic strength. He was like a genius. He was a blind genius, I would say. Anyway, I learned a lot from him, and thank you. So here is about the same time, maybe later, a few years later, actually. That's the whole company. That's me, that is Gribov, that is my father, Arkady, and that's Okun. So Okun and Gribov were actually something like students of my father. And that's, by the way, is Sydney Drell, which means that was Soviet-American symposium somewhere in Armenia, because these people are from Armenia, and that's Leonid, yes. So what Strickman, and that's what's that? I forgot his name. Anyway, so these are two physicists from Gribov School from Leningrad. So what are we doing? We are playing push game. Push game is when you stay on the ground with your feet tightly together, and you're supposed to hit other guys' palms in such a way that he will have to make a step. He will lose his balance. And of course, I was much stronger than Okun, but he was so tricky, and he was fast, and he was just didn't want to lose. And I don't remember the score, but it was something like equal. When I managed to hit him, he stepped because I was heavier and stronger, but when I didn't, I lost my balance. So he tricked me into losing my balance. Anyway, that was fun. That was a very fun time. That was one of the first Soviet-American symposia. We were discussing together. We were drinking good wine. We were, having fun time. In spite of the fact that there was still no theory of elementary particles, there was still this conservative Landau School of Gribov and Okun, who previously, before that, totally killed our theory with Sasha Polyakov and humiliated us at the sessions of the Academy of Sciences. Still, we were working together as good friends, We were all serving the same goal. Anyway, so anomalous dimensions. So that was the first expression of the idea of anomalous dimensions as eigenvalues of the field theory equations. Now, this idea evolved. Kadanoff was playing with this idea very early. He was playing it in a very simple examples, but that's important still. He was playing with Ising model and thought about he thought the dimensions are rational numbers. He couldn't think that they could be irrational. He even lost a bet. I bet with him that anomalous dimensions are irrational numbers, and he lost his bet because he bet that they are rational. Because after Ken Wilson discovered epsilon expansion, it became clear that at least in 3 dimensions, anomalous dimensions are not rational numbers. So I had my ideas for normalization group equations, and here I am defending my doctoral thesis, and that's the bold head of Khalatnikov. I'm defending my thesis, and my thesis was explicitly involved to a normalization group and scaling dimensions and the idea of the, called the scaling indices. I didn't have the term of, it was something like 73. Of anomalous dimension. That was advance of Ken Wilson. But anyway, he read that paper, and he said it was a good try. It didn't work. It is true. So that was the idea of normalization group equation. But he brought that idea to perfection. He understood the global meaning, not just local meaning of normalization group as a scale transformation, elimination of degrees of freedom. And then he also developed the epsilon expansion, which was just a trick, but such a brilliant trick that it impressed everybody. He got, Nobel Prize, though maybe prematurely, because that was not the end of story. The real end of story is the conformal bootstrap, and the final kind of score was done by Slava Rychkov following work of my old work on conformal bootstrap, old bootstrap, then Sasha Polyakov's new bootstrap, then operator product expansion. So that is something much more, deeper, much deeper, I would say, than epsilon expansion. But anyway, Ken was the first one who understood and presented these ideas to the world. So I still think he's such a genius that he deserved the Nobel Prize. If not for that, then for lattice gauge theories or some other things. Anyway, so let's now talk about modern conformal field theory. Next step in developing anomalous dimensions was Sasha Polyakov's observation that the conformal field theory, which technically existed at that time, conformal-invariance was known, and it was formulated at the kinematical level by Gross and West, I think, by some other people, Mack. I'm not sure who was exactly the first who formulated that, but that was at the perturbative, at the, without idea of anomalous dimensions. Sasha Polyakov combined that with the idea of anomalous dimensions in 71 and derived his famous formula for the 3-point function, which is the product of triangle side of the 3 points raised in anomalous powers. And that formula led me to simplest form of operator product expansion in 71, and then Ferrara Gatta-Grillo elaborated on that work and derived the most general conformal operator product expansion. I must say that this story is kind of hidden in the dark. The fact is that I sent the paper in 71 to Physics Letters, and in that paper, in the end, there was this conformal operator product expansion, though in the simplest case. It was said, okay, from conformal 3-point function, you could derive the operator product expansion. Here it is for the particular case. Now, Gatto was editor of Physics Reports. So he was so impressed with my paper that he asked referees Ferrara and Grillo to elaborate on that. So they sat on my paper for a year. And meantime, Ferrara, Gatta, and Grillo published their own work in 71 without citing mine. And there they developed the most general form of operator product expansion, which now is known as operator product expansion of Ferrara and Grillo, or Ferrara-Gatta-Grillo. I felt very bitter about that because I made discovery and I was kind of raped by gynecologist in the chair. So I complained to Gatta, and he apologized to me later, but it was too late. I am not going to fight for my priority, but it's there, it's published. It's just not cited in the work of Ferrara, Gatta, and Grillo. Anyway, they did it in most general form, and it's very useful. So they did something very important. So yes, just they should have quoted me, and they shouldn't have sat on my paper. So old bootstrap was the idea, like I said, that you just have a skeleton graph expansion, and each term of skeleton graph expansion has the same scaling order. And now with conformal three-point function, each term of skeleton expansion can be computed to exactly same conformal amplitude times some unknown numerical factor, and that numerical factor depends on the dimension, and equating left and right side, you get, self-consistency equation like I dreamed up in 66. And moreover, I present examples in that old bootstrap. Basically, if you consider a large 1 over n expansion, the only leading term in the three-point function in that old bootstrap would dominate. So there are cases when indeed skeleton graph expansion makes sense, so that indeed old bootstrap can produce results. But of course, that pales in comparison with the new bootstrap, because what was observed by Polyakov in 74 and finished by Ryczkow, who presented it to the beautiful theory called new bootstrap. What was observed by Polyakov in 74 was the fact that just the crossing symmetry of the four-point function by itself provides equation for the indices. He demonstrated that in terms of epsilon expansion, but that was just an important fact that if you take the midpoint between the 4 points, such a configuration where both expansion in one channel and in another channel makes sense, you could compare the expressions for operator product expansion for the 4-point function in two different channels, and both of these expansions overlap and must work in the middle, and then that provides equation for indices. What Ryczkow did in 2014 was very important observation, but there is extra information you could add to those equations, which is positivity of the measure, because it's not just arbitrary function, it's some average of product of operators in the theory with Hilbert space, and there is a positivity there. It is the theory with permission Hamiltonian, so there is certain inequalities. So if you add the positivity constraint to the crossing symmetry equation, suddenly you get the workable scheme by means of the linear programming or quadratic programming, which you could solve. And that led to much more precise expressions for the indices than Wilson's epsilon expansion. And what is more, it involves the true dynamics, the true conformal symmetry, operator product expansion, so that it's a microscopic theory. It's not just an extrapolation of expansion. So in my view, this is the theory of critical phenomena. So that's a final step in a very interesting and dramatic story, which started with attempts to rebel against the dogma of asthmatics and the ban on the microscopic theory, and that ended up with the Higgs effect, with gauge theories, QCD, and conformal field theory. All of these became the most important part of the modern elementary particle theory, except, of course, for quantum gravity, which is still a terra incognita. But anyway, this is a happy end of that story. Now, here are the heroes of that story. That's Sasha and me, sometime in early 80s. That's, again, Sasha Polyakov. That's me behind him. And that's Volodya Zakharov, another, great scientist, late Volodya Zakharov from Landau Institute. So we were hiking in the Fan Mountains, and that's a 15,000 feet mountain. We're on the top of that with some unknown girl whom we picked up on the way to the summit. Anyway, we're laughing. The photo is made by the companion of that girl whom we asked to shoot us. So, but she doesn't seem unhappy. Anyway, that was fun time. This is Slava Rydkov, who scored the goal in this conformal bootstrap game. And so that is how the modern conformal field theory was created. And I didn't even mention the two-dimensional version, which became part of mathematics because it nicely fit into the other developments, Kac-Moody algebras and other developments, models of Fermat and other developments of modern mathematics. So two-dimensional conformal field theory is actually part of modern group theory. It is finished theory. Three-dimensional and four-dimensional conformal field theory are not so simple. They are still being developed, but the three-dimensional version is already in the stage where you could compute things. Four-dimensional is still at the stage where you could solve some cases, but not all of them. There are remarkable analogies between conformal field theory and gravity. It's called ADS-CFT duality. I'm going to mention that in the second half. So, second half starts with
Migdal.
Oh?
I was wondering, I have a few questions I wanted to ask.
Yes, you may ask questions about field theory, yes.
Yeah, so I guess my first question is, before you were talking about the Higgs mechanism and, there's this whole relation between, critical points and, sort of critical phenomena, condensed matter physics, and all these kind of things. And the context where you and Gribov developed this is in, region field theory. So I was kind of wondering about kind of, cross-fertilization at the time, where people I'm assuming people were not just only reading, particle physics papers, but also, papers in other fields. And it seems that in that time, at least in the USSR, there was a lot more cross-fertilization, whereas you were mentioning with the S-matrix dogma and, Geoffrey Chew and this whole idea of, nuclear democracy. And, he was very adamant that, there would be some ultimate S-matrix theory and, you can just forget about field theory. But it seems there was a lot more, you guys at least were interested in quantum field theory. So I was kind of wondering, where did the defense of quantum field theory come from? Was it from, critical phenomena and condensed matter theory? What's kind of the relation between, why you didn't just, agree with Gribov and all the rest of the people who criticized you?
That's a long question. I'll try to answer it with a short answer. So the S-matrix theory was initiated in the West, but basically the death of the field theory was initiated in Moscow. In the end, there was Landau School at that time was firmly on the side of the S-matrix theory. That was Gribov and his school followers of Landau. Now, there was still some pockets of resistance in Soviet Union, and I could count them on the fingers of one hand. That was, Ludwig Fadeev, that was Fimov Radkin, that was, who else? Vax and Larkin, and us. So we were kind of guerrilla warriors, or we were underground, we were dissidents. And, in spite of Landau School being something kind of progressive and bright, it was also, it inherited some style of Stalinist era. When they thought something was right, like Stalin did, by the way, then when they thought something was right, they fought with opponents, and they didn't hold their punches. So we were trying to object to that, but basically it was heresy. Yes, it came from the West, and it was developed further by Gribov and the whole ETF school. There were people who were doing that for decades. They took that philosophy that you should study asymmetrics. That's what was our teachers were teaching us that. So yes, field theory was almost forgotten, and there were just few pockets of resistance. We were lucky that my father was independent thinker, and so was Larkin, who inspired us to work on that. Did I answer your question?
Yeah, thank you.
Okay. Any other questions?
Hi, I have a quick question. So in your paper with Polyakov in 66, would this be the earliest published paper on the non-abelian Higgs mechanism as well? Because this predates Kibble's paper in 67.
No, our paper was held in the JATP editorial for 2 years, so it was only published in 66. But there were 3 submissions, 64, 65, and 66. So the earliest published paper of ours is 66. The paper of Higgs and others were published in the end of 64 and was submitted in the summer of 64. So we submitted our first version either at the same time or slightly earlier. I don't remember exactly. There is no way to find. It was independent work, but our methods were different. He was considering field theory, and we were considering the non-perturbative version with diagram technique, but the results were the same. So I am not trying to claim that we deserve Nobel Prize. No, we missed the boat. We couldn't publish our paper, and as we say in Moscow, almost doesn't count. So we almost did it, but we didn't. So it was deserved by Higgs and Engleton-Brout. So we're not trying to claim otherwise.
But I thought the earlier papers were all for abelian groups, and your paper will be the first one on non-abelian groups. Is that correct?
I was not sure. I think that non-abelian were also studied. Yes, our paper was definitely SU2. Yes, but that doesn't matter. Mechanism is mechanism, and I think I think the Engler and Brout were non-abelian also.
Oh, I see. Because often, like in classes, we were taught that non-abelian Higgs mechanism was credited to Kibble in his 1967 paper, but
look, I can tell you one thing. We were so humiliated by Landau School that we didn't even try to remember that. We were stomped to the ground, and that was the end of it. The paper was published, then we found out that we were late because it was published before, and so the objections of Landau School were ridiculous. But then everybody was so much against us. Nobody wanted to discuss it. So until the QCD and until it became obvious to everybody, there is this standard model, etc. Until that, nobody would want to talk to us about spontaneous symmetry breaking. And after that, they jumped into that, and they forgot that we were talking about that a few years before, and we were kind of discouraged. We were working with conformal field theory at that time, so we didn't recall, we didn't, request recognition, so we were just busy with other things, more fun.
I see. Thank you.
More questions?
I think I just wanted to make a comment. I think regarding the abelian versus non-abelian, I think the second of England Brout's papers dealt with the non-abelian case. The other thing I wanted to say was I was curious about about this idea of conformal. You mentioned 2D conformal field theory, and the famous BPZ paper appeared in 1984. And if you look at a lot of the literature they cite, it's like dual models, it's papers from this period. And I was kind of wondering, it seems all of the ingredients for that paper were in place by 1974, but the paper appeared 10 years later. And I was wondering, perhaps you could say something about why the delay with that paper, or what people were thinking about 2D CFT?
People did not understand that the statistical field theory and theory of elementary particles are one of the same. That was psychological barrier. The only person who really understood that was, I think, Phil Anderson, who indeed explicitly said that he thought that this mechanism of suppression of the Goldstone, of exception from the Goldstone theorem in case of Coulomb forces applies to Young-Mills theory, but Young-Mills theory didn't really exist at that time. See, it was just speculation. So we came at the right point and right time with ignorance and bravery of youth, and we were inspired by Tolle Larkin, who understood that also. So we did not think about objections, and we just said what we wanted to say without much thinking. So that helped, because later, we couldn't know that at that time, but later it was proven that gauge theories exist and can be quantized, they're anomalous. Well, that was not known at that time. We were just waving hands. So that was a case of intuition. Part of that intuition was intuition of Tolle Larkin. Another part was our own. But basically, we were the first boy who said that emperor has no clothes. We were just saying something which smarter, older people suspected. And we were the first to actually say that. Any questions? Maybe I will switch to the second part then. I take it as an agreement that there are no more questions about the first part, and I will switch to the second one. So loop equations. Let me start with loop equations. It was the first loop equation in QCD was derived with my student Yuri Makeyenko in 1979, and then it was developed with students Volodya Kozakov and Ivan Kostov in the early 1980s. And it was then applied to triangulated dimensional gravity by Volodya Kozakov, and then it was solved completely by means of matrix models by 3 independent works: Kozakov, Brzan, Schenker-Douglas, and Gross and myself in the 1990s. And loop equation became the major non-perturbative approach to gauge theory and turbulence. And these are the people involved in that. That's Yuri Makeyenko, that's me and Volodya Kozakov near Notre Dame. It was intact at that time. Now that's David Gross, younger David Gross. That's younger Eduard Brzan. That's older version, I couldn't find younger, of Ivan Kostov. That's Mike Douglas, and that's Steve Schenker. Now, what is the meaning of loop equation? Loop equation is a way to reformulate the gauge theory in gauge invariant terms as dynamics of the circulation around arbitrary loop. Turned out that circulation and its quantum, its non-abelian analog, which is called Wilson loop, is trace of parallel transport around the closed loop. That object being considered as a function of the shape of the loop turns out to satisfy a closed equation. And that's very important because, first of all, it's only relevant degrees of freedom, gauge invariant. And second of all, that's reduction of dimensionality, because that basic object is loop, and loop is one-dimensional object. It's a vector function of one variable, which is angular variable along the loop. So that's some way of solving theory by going into higher dimensional space where suddenly it reduces to the lower dimension. So that's the beauty of this loop equation, and also enlarge and limit of QCD, it becomes classical equation, no longer chain of multi-loop equation, just one classical equation. And that's an important thing. There were some models and there were some numerical methods. So it became non-perturbative, measured non-perturbative approach. And in particular, it was some extension of that led to exact solution of two-dimensional gravity. So I'm going to talk a lot about the application to turbulence. I'm not going to talk about application to gauge theory because it's not finished, frankly. It's just recently the good numerical methods are developed, but it's not the end of story. So I will talk about another story which started in '93, and that story have happy end. Now let me switch to that one. Let me switch to that story. Okay. I call it quantum solution of classical turbulence. And that's a recent work, so that you don't think I'm just the old guy who is remembering good old times. That's something started in '93 and finished in 2022/2024. So here's the introduction. So our generation of theoretical physicists is accustomed to building and solving models based on existing physics theories. And these foundational theories, classical mechanics, statistical physics, relativity, quantum mechanics, and quantum field theory, were all developed in the previous centuries. It's like in this Hermann Hesse book, Game of Beads. We are just playing with something we don't invent. Well, there is one glaring omission: statistical field theory, statistical theory of turbulence, still missing. It should be something similar to, quantum field theory, which is quantization of the field, classical field equations. So we have classical equations, Navier-Stokes. So what is statistical field theory? Statistical theory of turbulence missing. This theory must be built from Navier-Stokes equations without model assumptions such as multifractal scaling laws, just like Gibbs-Maxwell statistics and quantization of field theory. It's a general theory, not model. Once constructed, it must be solved and then compared with experiments. That's what we modern theoretical physicists are good at. We're good at solving models, but now we have to first build the theory and then solve the model. So the turbulence problem looks deceptively simple. And by the way, I know it would annoy many experts, but I say, to understand what I'm going to talk about, you have to forget all the 80 years of recent development of turbulence theory, because that's a sidekick. That's a turn which was missed 80 years ago. Anyway, the turbulence problem looks deceptively simple. Find the limit of solution of Navier-Stokes equation when viscosity nu goes to zero at fixed energy dissipation rate. And here is the Navier-Stokes equation, time derivative of velocity. There are two terms: curl of vorticity times viscosity plus cross product of velocity times vorticity, and minus gradient of thing called enthalpy. And that gradient term actually drops in the, because that's potential term, that drops in the loop equations in dynamics of vorticity. And then there's, of course, incompressibility condition, which is extra, not dynamical, it's extra condition at any moment of time. So instantly, the pressure actually adjusts to the velocity such that at every point in space, instantly, this equation, divergence of vorticity equals zero, is satisfied. Now, in this limit, when viscosity goes to zero, the Navier-Stokes equation tends to the Euler equation everywhere except some singular regions, vortex filaments. These regions are randomly distributed in space, making velocity and vorticity stochastic variables at every point, with local vorticity values divergent in the turbulence limit. So there are randomly located filaments with strong vorticity. Without viscosity, that would be infinite, but with viscosity, they are inversely proportional to viscosity. And locations of these vortex structures is random. They are easily moved one around each other in the common self-consistent field created by all these vortices structures, because each vortices structures has a long-term so-called Biot-Savart law, and they all add up and contribute and move around, move every one of them around. So here's a picture of the vortex filaments in the turbulence. You see, it's a very complex picture. They're all intermingled, and they are all arbitrary shape, and they are all over the space like the soup of spaghetti or whatever. It is something very difficult to describe if you try to do it in terms of initial variables, velocity and vorticity. How can you describe such thing? Well, you could try statistics, just like with molecular dynamics. Molecular dynamics is also complex. There is all these trajectories of all these molecules in the gas, but still there is a Gibbs distribution which describes that statistically. You don't want to follow each trajectory, you don't want to follow each structure, you want to describe statistics. You want to describe the observable things which are averages of all these random distributions, and that could be as simple as this is complex. The idea, of course, is that statistics becomes much simpler when the dynamics becomes much more complex. It's opposite limit. And that's how the problem should be solved. You should not try to hit your forehead against the wall. You should find the way around the wall, because behind the wall there is a simple garden with flowers. You didn't really want to climb that ice wall. So Hopf outlined in 52 the general statistical approach to the turbulence using the functional. It's called Hopf functional. It's exponential of convolution of some external current times velocity field. So this thing is treated as a function of this external current or source can be used to generate correlation functions of velocity. And yeah, that's a good idea, except it didn't really work because it's very complex. This functional generates the correlation function of velocity field and satisfies the functional differentiation equation of the form. Time derivative of this z is some operator which depends on the source, and functional derivatives with respect to source applied to the z. So it's rather straightforward. You find time derivative, you note that the source is time independent, but the velocity depends on time. You differentiate exponential, you use Navier-Stokes equation, and then you get each term you could express in terms of either source or velocity, which is functional derivative of the spectral source. So it's rather straightforward exercise to derive, using Navier-Stokes equation, to derive the Hopf equation. It is linear with respect to z, which is remarkable, but it's three-dimensional, and it's so complex that nobody managed to solve it. And so the turbulence corresponds to the degenerate fixed point of Navier-Stokes dynamics. In the same way as Gibbs distribution is the degenerate fixed point of Newton dynamics, uniformly covering the energy surface. So similar equation in the Newton dynamics can also be written, of course. And then you want to find the fixed point. That's solution when z is in equilibrium, when time derivative is 0, and that's eigenvalue of that operator, and it's known what it is. In case of Gibbs distribution, it is solution of that equation, and solution is just exponential of arbitrary constant beta times Hamiltonian. And why? For a very trivial reason, because time derivative of Hamiltonian is 0, and Hamiltonian is additive. Therefore, exponential of something times Hamiltonian is multiplicative, as it should be for different parts, and that is conserved. So Gibbs distribution is rather trivial solution of the Hopf equation, and it's a true solution, that's statistics. Now we have to find the same thing for the Navier-Stokes, and the equation is different this time. Energy is not conserved. We have to dream up something else. We have to find different solution. Well, what happened is that decaying turbulence, which is actually solution of that equation for Navier-Stokes, is a degenerate fixed trajectory, slowly approaching stable fixed point at zero velocity due to friction forces represented by vorticity. Let me elaborate on that. You see, energy is not conserved. So we know that whatever initial energy there was at initial moment, during the evolution, velocity would eventually stop because all the energy, which is integral of v squared, will dissipate, and the velocity will have to tend to zero if integral of v squared is zero. And then that trajectory might become universal. In the end, when all the initial data are forgotten, that approach to zero may follow some universal degenerate fixed trajectory. So that would be decaying turbulence. Degenerate fixed trajectory slowly approaching stable fixed point on zero velocity. So we need to find that. Now, Hopf equation for the Navier-Stokes dynamics is compatible with such a trajectory, but it is too general and complex to compute anything beyond the large viscosity expansion, which is opposite in turbulence. So the only thing you can do with Hopf equation is to expand in inverse powers of viscosity, which is essentially expansion in terms of nonlinearity. First, we start with neglecting nonlinear term, v cross omega, and then, of course, solution is rather trivial, that's diffusion, and then you elaborate on that. And then once you do that, you get every term would contain negative powers of viscosity, which means that for large viscosity, that is a good solution, and that is and that solution is basically laminar flow, and then not laminar flow, it's a viscous flow, okay? Viscous laminar flow without any turbulence. So it's not what we are looking for. So we need to find the solution of Hopf equation in the opposite limit. Now, complexity of the Hopf equation is equivalent to the non-Gaussian functional integral because it has three-dimensional source. So if you have functional equation in terms of three-dimensional functional derivatives, that would basically be equivalent or even more complex than functional integral, which has three-dimensional fields. And attempts to write such integral were tried. It's called, it's called wild functional integral, but that doesn't work. First of all, it doesn't look to describe correct phase, which is turbulence. And second of all, it is impossible to compute. Nothing can be done. Nothing useful can be done with this wild functional integral. The best try was our attempt to compute the instanton, but that instanton turned out to be non-universal. It specifically depends on the structure of the correlation of random forces. So it's not what the fixed point we're looking into. Anyway, forget the wild integral, forget the Hopf equation because it's too complex. We have found a solvable replacement of the Hopf equation, the loop equation. Now decaying turbulence can be solved in quadrature, not functional integrals. So we have, the audacity of presenting exact solution of the decaying turbulence problem, and I'm going to present it right now. So loop average is a particular case of the Hopf functional with the source concentrated on a fixed loop in space. So you take the source, which is integral around some loop of three-dimensional delta function of r minus c. So that delta function is three-dimensional. If you could eliminate one of three delta functions, and then you will get delta function of transverse deviation from the loop. So basically, this source is concentrated around the loop, along the loop. Everywhere outside the loop it is zero. Along the loop is basically proportional to the tangent vector of the loop. Now, there is this notorious factor of I, where it's imaginary unit, and there is arbitrary dimensionless parameter gamma. So loop average is defined as average of exponential of integral of this source, so which is average of exponential of some factor times circulation, and circulation is integral of the velocity projected on the loop around the loop. And that's a very well-known object in, fluid dynamics. Velocity circulation doesn't depend on potential part of velocity, only rotational part, because there is a Stokes theorem by which you could relate this circulation to the surface integral of vorticity, so potential part drops. But still there is a closed equation, which is remarkable. That means that Hopf equation was too general. So this object, loop average, can be studied, and we derived certain closed functional equation, which is similar to what we did in gauge theories. So if you find time derivative of this loop functional and use Navier-Stokes equation, that's Navier-Stokes equation for the time derivative of circulation, the last term with a gradient drops after integrating over a closed loop. Now both of these terms can be expressed in terms of functional derivatives with respect to the shape of the loop. So this can be written as integral over the loop of some operator which involves functional derivatives with respect to shape of the loop acting on this same function. So we get analog of loop equation, but our operator is much simpler because it's one-dimensional now, because we only have functional derivative with respect to function C of one variable, not source depending on three variables, with suddenly reduced dimension of the equation. And that's something which has very far-reaching consequences. Now, and that's exact equation, no approximation made. So this operator L only depends on the functional derivative, but does not depend on the coordinate C in the loop space. So L, you see, analogous operator in case of the Hopf depended both on the source and functional derivative. This one only depends on the functional derivative. This independence, which means translation invariance in loop space, is the key to the solution. If we would add external sources, we'll break it. So I'm not talking about external sources in this talk. It's the subject of the next year's talk. I'm still working on that. But this case, decaying turbulence, no external forces, it's a solvable case because this operator doesn't depend on the coordinate, just on the derivatives. So this equation is equivalent to the Schrödinger equation in loop space with the Hamiltonian, which is integral over the loop of some operator depending on the functional derivative with respect to the loop. Now, if we consider the loop as a point in our space, it's called loop space. So this operator, functional derivative with respect to the loop is like momentum. If the loop is the coordinate, then the functional derivative with respect to the shape of the loop is momentum. So we have an interesting situation. We have the Schrödinger equation where the operator essentially, Hamiltonian essentially depends only on momentum, doesn't depend on coordinate. That means the plane wave would solve it. That's simple. Here is the solution of the loop equation corresponding to the Schrödinger equation. Exponential of integral over the loop of some function p, which depends on theta, but not on the shape of the loop. There is only one dependence of the loop, which is here, and here it's something which does not depend on shape. And this whole thing is what's called symplectic form. It's correct parametric invariant analog of coordinate times momentum. So the plane wave is exponential of IPX, where p is momentum and x is coordinate, so analog of that is this. And that thing satisfies the equation. It just passes through equation. When you substitute that equation, you will get equation for the p. So you will get equation time derivative of p equals that same operator L, where instead of the functional derivative, you'll have just this p, differentiated, of course, because it's in order to find functional derivative with respect to c, you should integrate by parts, and then you get time derivative, theta derivative of p. So that is what you get for the p. So far, it's all exact. It's something which could have been done 250 years ago. It's just transformation of the Navier-Stokes equation. Now, here is this equation. That's exact equation. Time derivative of p, proportional. There are two terms. There is one term and another term. So this term as a vector is proportional to p, and this term as a vector is proportional to delta p. Now, delta p is, by definition, discontinuity. Yes, this is a field, is a fractal field. It has this continuity at every point. So there is this continuity, delta p. And p by itself is 1/2, as usual in Fourier analysis, 1/2 of left and right limit, because there are discontinuities. So that's exact equation. And it looks horrible, very difficult, but there are two beautiful things about that equation. First thing is that there is no explicit time dependence. And second thing, there is no explicit theta dependence. There's parametric invariant. This equation is parametric invariant, and it doesn't have explicit time dependence, so one could hope to solve it exactly. And that is the case. There is exact solution of that equation. Not exact solution for arbitrary initial condition, but exact fixed trajectory of this equation. So there is exact solution of this equation, which, given initial condition, hopefully would be approached at large enough time. But that's not approximate solution of this equation, it's exact solution of this equation. It just doesn't satisfy arbitrary initial condition. So this nonlinear equation can be solved analytically. The mathematical details are too complex to present here. And frankly, they are too complex to the most members of the turbulent community. Only people from mathematical physics and string theory and quantum field theory community understand it. But these people, unfortunately, are so busy with gravity and conformal field theories that they cannot get their attention, because they think the turbulence is something so dirty that they shouldn't even look at it. So there is a gap. But anyway, I hope that gap will disappear soon. So here is the resulting formula. I'm skipping like a light year of computations. And here's the result. So that equation was solved. The limit, continuum limit, was taken, and there is a result explicit formula for second moment of velocity difference. Second moment of velocity difference is something kind of notoriously famous in the theory, because Kolmogorov said that must behave as distance to the 2/3. That's Kolmogorov scaling. Don't mix that with the expression for the 3-point. That is a correct expression which nobody could modify. But any other moments, like the 2-point function, according to Kolmogorov, must scale as a simple power of distance, 2/3. And that's called such a fundamental law. For 80 years, everybody was praying on that, and nobody dared to object, though, in fact, the emperor has no clothes. So that's our answer for that. It's complex, it's non-trivial, so-called Mellin integral, which has a ratio of coordinate to the square root of some parameter nu tilde, which is the only parameter of our theory, times time. So that's this variable, dimensional scaling variable, and there is 1/t here. So what is really remarkable is that this Mellin transform V of p has ratio of Riemann-Zeta functions, and also some trivial, polynomial functions. So, and this f is some calculable entire function, which is computed using Mellin integrals of elementary functions. So function f is not important because it does not affect neither zeros. I mean, it doesn't affect poles, which are all what is relevant here, because the scaling behavior of this second moment as a function of distance is determined by the poles of Mellin transform, the spectrum of anomalous dimensions. So we were dreaming. So, you know, in critical phenomena, there was a feat of finding spectrum, approximately finding, computing the spectrum of anomalous dimension. Here, I present explicit analytic answer for spectrum of scaling dimensions in decaying turbulence. And I will show that in a minute. They are determined by the poles of this function v of p, and entire function doesn't affect that poles. So what are these poles? So here is a spectrum of poles. So negative ones are not interesting because we're considering small behavior, small distances, and therefore only positive poles contribute to the asymptotics. So there is trivial series of even integers, starting with 2. Then there is the next one is 5 seconds. And then the next one is 11 seconds. And the third one is very interesting. It's 7 plus minus I times t, where t are imaginary parts of zeros of Riemann zeta function. And then there are other poles which start with 15 halves, etc. So these are very explicit formulas. Who would think that one could compute the spectrum of scaling dimensions? Moreover, who would think that there is not just one scaling dimension which corresponds to some scaling law, but the whole infinite spectrum? So there's no such thing as scaling laws because there are infinitely many scaling indices. It's a quantum scaling indices. So T are imaginary parts of Riemann zeros. And imaginary parts of dimensions lead to quantum oscillations because we have a non-Hermitian theory. Turbulence is not a statistical theory. It's a decaying, it's a, you know, on equilibrium, decaying turbulence. It is not, but that's the whole point. Otherwise, that would be simply Gibbs distribution. It's not. It's something new, quantum. So let me briefly mention Mellin transform of energy, and it's related to a similar function and has a different spectrum. And here the spectrum starts with minus 5/4, and then there are other similar points in complex plane. So here are experimental data obtained in 1966. And they basically say that if you consider that's inverse energy as a function of time. So energy decays as time to the minus 5/4. So 1/4 energy grows as time to the 5/4. Now here there are two energy, longitudinal and transverse, because that's a so-called grid turbulence in a channel. So they are not exactly equal. There is a slightly different slope for longitudinal and transform. And the difference is, of course, the accuracy of the measurement. So average of these two is 1.25, which is exactly what we predict, 5/4. So that match. And nobody could explain that before. And Kolmogorov theory doesn't explain that. Now we did much deeper analysis. We consider what's called effective index. You take log derivative of second moment of velocity. So if Kolmogorov was right, this log derivative of second moment should be exactly 2/3. Okay, and in fact it can be related to the energy spectrum, because energy spectrum is related to the correlation of velocity fields. So all that in Fourier space is this integral. You could take experimental data for energy spectrum, which are measured in numerical simulations, and compute these integrals, and then consider it as a function of time and average over time and find the errors. So this function is very well defined numerically, and that's what we get. So here are three curves. So Kolmogorov scaling law, which says it's 2/3 is this blue horizontal line. And on the x-axis is a logarithm of ratio of coordinate to the L of t. L of t is effective length. And I separately verified that it exactly satisfies our prediction, which is the square root of t. So once you find the scaling variables, then all the points for different coordinate and different time collapse on a single curve, and the thickness of this red curve indicates the errors. They're so small that you don't even see them. You don't even see the red curve. And why you don't see it? Because it's exactly covered by the theory. My theory totally fits, goes through all these experimental points. So unlike Kolmogorov, which is totally off the charts, my theory, which is this formula I presented with Riemann functions, exactly goes through all these points. So there is a perfect fit between agreement between the theory and numerical simulations. And total refutal of the Kolmogorov theory. So whatever was dreamed up and considered by laws of turbulence for 80 years was a myth. It's wrong. But here's correct theory. So here is what the summary of this work. So there is duality, which I didn't describe, but in fact, in the paper, it's much more than just solution of some equation. There is duality between decaying classical turbulence in 3+1 dimensions and one-dimensional quantum theory of Fermi particles in a ring. Because the way I solved this loop equation, I reduced this to certain one-dimensional quantum theory of Fermi particles. The density fluctuations of these Fermi particles disappear in the turbulence limit when viscosity goes to zero, inversely proportional to the number of the auxiliary points on a circle. So I consider the loop as a limit of polygon with n sides, then I should tend n to infinity, viscosity to zero, and in the limit I lead exactly, I have exact computation, and it determines some instanton solution for the density of these fermions. So basically, I reduce strongly fluctuating velocity field to the dual theory of weakly fluctuating Fermi particles, and that's how I can solve it. This establishes a new relation between classical nonlinear dynamics and quantum theory. And the way that relation works is that Fourier transform of classical probability adheres to quantum mechanical evolution with the interference of alternative histories. So what I'm claiming is that this solution means that there's a hidden quantum mechanics working in turbulence, because my solution is exactly equivalent in a dual sense, exactly equivalent to the quantum mechanics of the one-dimensional ring of Fermi particles. So it looks like a classical theory, but its Fourier transform of classical probability is in fact quantum mechanical amplitudes. You just didn't know that when you open your faucet and see the turbulent flow. You don't know that the Fourier transform of probability for circulation in that flow goes along the quantum mechanical evolution with interference of alternative histories. It's just the result which you see. Okay, time to the -5/4. So the spectrum of the turbulence scaling dimension is related to the zeros of Riemann zeta function. There is unexpected relation between turbulence and number theory. And the grid turbulent experiments and recent dynamical simulations rule out Kolmogorov laws, multifractal and Heisenberg scaling laws, but confirm this theory. So that's the end of this presentation. Questions, please.
I was wondering
If
if you
somebody
could,
wants to curse me for spitting on the icon of the turbulence theory, go ahead.
I was wondering if you could say something about the relation of your theory to Polyakov's sort of conformal turbulence and other kind of approaches like that.
There is no relation. I believe that there is no conformal symmetry in three-dimensional turbulence. And the reason is very simple. If there would be conformal theory, conformal symmetry, then velocity, which is a three-dimensional conformal vector field, should have dimension d minus 2, which is 1, and in fact it has dimension close to minus 1/3. And moreover, vorticity, which is also a conserved three-dimensional field, should also have the same dimension. But velocity and vorticity is a curl of velocity, so they couldn't have the same dimension. So literally, conformal field theory doesn't apply to turbulence. And the reason, by the way, is incompressibility. Because of incompressibility, there is non-locality. So there is non-local relation between various scales. So conformal symmetry implies local scale symmetry. And that doesn't work in case of incompressible fluid because pressure has the integral over all scales. So pressure violates this. There are no scaling laws. Yes?
So you mentioned that this like poles of the zeta function correspond to like effective spectrum dimension. There is something that we found in disordered systems where, particularly neural networks and like statistical systems, where behavior of them in this new like deep regime is determined. Well, it's not something that we found. It's something that Watanabe found. It's something that we study. The scaling laws determined by algebraic geometric invariants of these singularities that appear in like the ground state. I was thinking if are there any like associated algebraic geometric properties of these singularities in this? And I also have another question about the Riemann zeta function, but I'll ask it a bit later.
Okay, answering this question, I was told already that there are some statistical systems where the spectrum, energy spectrum, is related to zeros of Riemann zeta function. I think that was first discovered by random matrices by Dyson, that indeed there are some disordered systems where the spectrum is related to Riemann zeta function. Riemann zeta function is such an universal concept in in number theory that it's not surprising. But let me point one thing. All the systems they're talking about are quantum systems. This is classical system. So the fact that you have any relation to number theory is entirely due to the analogy between loop equation and quantum mechanics. Once you have quantum mechanical system and you are considering some spectrum, something, then indeed, once you consider a spectrum, whether that's a spectrum of energy or dilatation operator, then you might expect something like Riemann zeta function, any other number theory objects like Hofstadter butterfly. But the whole miracle here is that suddenly classical dynamics is related to quantum mechanics.
Oh, thank you.
I'm prepared to answer any provocative or unpolite questions regarding turbulence theory, because what I'm talking about is total heresy. I'm trying to claim again that the emperor has no clothes.
What do you think about like Thales entropy relationship to Riemann zeta?
About what?
Like Thales entropy, where like it's a non-additive entropy that became popular, where instead of using like Khinchin axioms, Khinchin, where they describe different entropy, and there is an additive axiom, the fourth axiom, which is that you can kind of just add systems, and Thales entropy gets rid of that, and it allows us to define kind of long distance interactions and account for them in these like long distance interactions, fractal systems, and it's like correlation functional corresponds to Riemann zeta. there is a zeta function for each like correlation functional from which we define this entropy. And Salas entropy specifically seems to correspond to Riemann zeta.
It's very interesting. Unfortunately, I'm not familiar with all these developments, but I can say one thing, is that when you're talking about conventional systems, you're talking about existing statistical systems described by Gibbs distribution or described by certain Hamiltonian. You have the fundamental theory behind that, which is either Gibbs or quantum field theory or quantum mechanics. This is the case when there is no such theory. There is only equation, which is called Navier-Stokes equation, which was not quantized. So the first step is to find what is the analog of Gibbs distribution, what is the analog of all these notions, and then you could talk about entropy, then you could talk about distributions and everything. So here I made that first step. I considered loop equations like Gibbs considered Newton equations. I'm not comparing myself to Gibbs, but I'm just saying that I considered Navier-Stokes equation in form of loop equation, and they found, amazingly, exact solution which reduces statistics of the turbulence to the quantum mechanical system. That's the moment when we have something like Gibbs distribution, and then we have to solve that model, go to zero viscosity, increase statistical limit, etc., etc. That is when we could talk about entropy and other things. It's not like we could borrow some, experience gained with conventional Gibbs statistical systems or quantum field theory systems, because this is new. This is something totally different.
Thank you all. Yeah, I just come into this from mathematics kind of perspective, so I don't know that much.
I would love to. Oh, by the way, I didn't mention that. What I did from the point of view of mathematicians, I presented a bunch of conjectures which have the physics level of rigor, which is basically none, but which are probably true. And that's a very interesting situation for mathematicians. When something which looks plausible and fits experiment needs rigorous mathematical justification, and moreover, it needs some understanding within the big context of mathematics. You need to find the correspondence of these specific cases with some more general objects. You could solve loop equations for arbitrary dimension. You could solve loop equations in arbitrary Euclidean or non-Euclidean space, etc., etc. There are many, many things which you can do, and in particular, you could understand the meaning of this Euler ensemble. What I'm saying, I didn't mention here, there is some very well-defined ensemble which I formulated. It's a number theory ensemble made of random fractions and some variables plus minus one located on a ring. So there is something very well defined in number theory, and a couple of number theories, Zakharescu and Bazak, actually wrote a paper following my previous paper on the subject. They wrote a paper where they studied that ensemble as it is and proved some theorems, made some calculations. They didn't find exact solution in the statistical limit that I did after, but I used their results to elaborate and go further. So there is the beginning of this mathematical study which would understand the meaning of this new object called Euler ensemble.
Thank you. This is very, very interesting work.
I will give, I think, well, there is a paper, long paper, not this small, just small slides, but the big paper, I will put it, make it available to the site so that it could be published on the site and people could look into that. It is also in all kinds of archives, Chaos and preprint, so you could look it there, but I will present the PDF manuscript just for you after this talk.
Thank you so much. Thank you.
Are there any other questions?
I have a quick question, if you have a second. Have you thought at all about applying this to compressible turbulence?
Look, there are several next things to do. One of them, of course, is compressible turbulence. Second of all is forced turbulence, which is, I would say, even the first step. That one, forced turbulence, I'm working on. I don't want to tell something until it is finished, but the stage of that work is I found exact solution for the forced turbulence as well. It's different from this one. It's not just simple rephrasing of this, it's totally different fixed point, but it's similar in spirit. It's also related to number theory, etc. So there is a solution of the forced turbulence, and that is also applicable to a wide range of phenomena. And then, so the next step after forced turbulence would be indeed compressible turbulence. And the next step would be plasma, because there is interesting situations when you have this plasma turbulence, and there are practical applications. And then there is a problem of approach to this solution. I found the fixed trajectory. Now, it looks like this fixed trajectory is stable because I verified that in numerical simulations. I just see how the solution approaches to the regime which I found, but that was not proven. In my work, in my previous work, I derived some generic equation for the spectrum of indices for fluctuations around my solution. So my solution, deviations from my solution decay or grow as some powers of time, and there's some spectral equation. So the next step would be study that spectral equation. So there's many, many things to do. And it's just the beginning. I invite everybody to jump in. I hope there will be similar thing to the what happened in conformal field theory, what happened in matrix models, when there are lots of bright young people who are equipped with all the knowledge of mathematical physics and who are hungry for the sophisticated problems which are worth their attention, and at the same time, unlike string theory, exist in nature.
Thanks for a very nice talk.
Thank you.
Yeah, if there's no more questions, thank you everyone for coming, and thank you, Professor Migdal, for giving this talk. We're very honored.
Thank you for listening, and your silence as well as your questions was very inspiring. And I'm glad I came to your forum, and I hope you'll keep doing that and keep inviting people, because that's a very good idea to let people tell the true story behind the story, because history is written by, well, you know, as let me quote Giorgio Parisi, who once said that in physics, all the credit goes to the one who is the last to make an important discovery. And that's unfortunately a bitter truth. Thank you.